significant time delay, maybe up to weeks until you have your measurement. So when we talk about process analytical technologies, our goal, of course, is always to have it inline. Not always possible, but from reality, here's our setup in the NGP Square biorefinery, where we have the usual controls and data sources like pH, we have temperature and pressure, etc. We have weights for our balances in order to collect the weight of the mass of acid, base, antifoam, etc. We have a gas analyzer. But we also have the possibility to add inline spectroscopy, Raman in particular, in order to analyze the process for more that what we can take or what we can derive from the standard analytical technique. The objective is, of course, here to collect data in real time, in our case, usually in the range of minutes, and monitor for desired and undesired changes, because we want to know in advance if the process doesn't go right. And so, of course, we monitor the relevant parameters like dissolved oxygen content, the energy intake of the agitator, oxygen uptake rate or oxygen transfer. That's what you can calculate also from the difference between input and the gas analyzer. The CO2 release as well, pH, of course, is not only monitored but also controlled, and temperature, pressure is usually set. Weight, simple thing, also, of course, the level of the fermenter needs to stay constant, or in terms, when you go for more complex feeding profiles, needs to be within the desired range. And it's, of course, validated with offline analysis. This is how we set up our process analytical techniques, in particular, Raman measurements or NMR measurements. How does that look like? NMR is something that you might only connect with chemistry labs. Now they have been able to scale that down in the last decade, roughly, to benchtop NMRs. They don't require any liquid helium. They have quite a small footprint, and they can use as a classical NMR, that would be an at-line machine then, which we regularly use in order to validate or get a first impression of what concentrations are there. But it can also be applied online. And here you see a setup here that is connected to a chemical reaction. Oops, sorry. So we have a tube here that allows pumping of liquid from a reactor or from a fermenter into the NMR measurement volume. Then the flow would be stopped in order to enable the measurement and pumped back again into the reaction chamber. That is a classical online application. It's not inline, but that's not possible with NMR in order to have the magnets around here. But what it gives you is a set of spectra here, where you see the shift, the NMR shift over time, and you can see that peaks are occurring or shifting just according to what happens during the reaction. The principle behind, I don't want to go into the quantum details here, but some atoms, in particular the protons, have a magnetic spin that can be analyzed here by NMR by applying an external magnetic field and excite that spin and measure the time basically that it takes to recover to its original position. And the NMR does exactly that, measures this frequency here, the signal over time, and then calculates a shift of intensity versus frequency, which is basically characteristic for a kind of shielded situation where the molecule is shielded by its electrons, and or the atom is shielded by its electrons, and due to the magnetic properties of the of the atom and its shift, you can identify clearly the moiety of that molecule, and it's also proportional to the number of molecules. So the area here under this frequency curve is proportional to the molecules that are in the volume of the measurement. So if you avoid to have metals in the measurement, then you're free to use NMR. A similar technique in terms of quantification here is then, but much more interesting, is Raman spectroscopy. Here you see some examples of Raman hardware that we are using. For instance, it's from Kaiser Optical System, now Endresen-Hauser, Tech5, Bruker. The first two are mobile and can be applied directly. The latter one here is a stationary FT Raman spectrometer. They can be connected to a process via optical cables, easily 5 to 10 meters, even up to 200 meters is possible. You can use immersion probes for inline process monitoring. Here you see some excerpts or examples. So everything from 6 millimeters is possible in a variety of possibilities regarding conditions, up to high pressure applications. And more interesting is the optical properties that they resemble. Here you can choose between different focal distances, depending on whether you want to analyze turbid mixtures or solid free mixtures, or whether you want to have a focus on serializable or heterogenic design. There are even non-contact optics available where you can look through windows and analyze from the outside of bioreactors, particularly important when it goes for single-use bioreactors, where you don't want to throw away the probe as well. So how is Raman spectroscopy, or what's the basics of Raman spectroscopy? In comparison to absorption, is much more complicated. So Raman employs a laser usually today that excites a volume inside a liquid. Could also be applied to a solid or to gases, but usually also with biotechnology, we aim for the analysis of liquid. And when we excite volume with laser light, we have usually scattered light that we all know. It's the same wavelength of the incident wavelength, and it's 99% more of the light is not modified in terms of wavelength, but a very small fraction is inelastically scattered. That's called the Raman radiation, and that's what we want to analyze. It needs to be catched by a detector, then processed by IT and or computers, and then gives us these lovely Raman spectra where we can follow, for instance, the decarboxylation, or in this case, the dissociation of acids. And that's then the objective of the quantification, to come up with some relevant figures there. In comparison to absorption, it's much more complicated. We don't have light that goes through a sample, and we don't compare the input or the light without the sample in comparison to with the sample, which could be easily related to the extinction coefficient, the concentration, and the length of the light that has been traveled to the sample. The detector is, in contrast, definitely not opposite of the incident light, because we don't want to collect the laser light, we don't want to collect the scattered light, the inelastically scattered light, and that's what you usually do in 180 degrees back scattering optics, or at a dedicated angle here around. And you have all the effects like turbidity, particles, blocking, deposits, etc. that can come also into play with Raman spectroscopy. The physical theory is here that you basically elevate the molecules to a vibrational virtual state, and most of the light is scattered elastically, like the Rayleigh scattering, but a very few amount is actually also bringing movement to the nucleus of the atom, and that is related to mass and energy transfer. And due to the fact that energy and mass transfer then always involves a loss of energy, you get some light that is shifted in its wavelength. And that's exactly what we detect here as Raman spectrum. There is in principle also the anti-Stokes scattering, which is not relevant in practice, I would say, but the Stokes scattering then gives you a Raman signal shifted to longer wavelength, thus lower energy in comparison to what the incident light has brought in. In principle, we would get scattering from every molecule, from every bond that is included in the molecule. However, it depends on whether the dipolarization, the change of the dipole moment is related to the molecular structure. That depends, or that determines whether it's actually a weak or a strong Raman scattering molecule. But we also face influence of color, organisms, impurities, particles, even fingerprints can make a difference on the vials or on the probes. So everything is in there, which is usually a challenge to quantify, but also gives you a possibility to determine more about the system than just concentrations. An effect that needs to be mentioned here is the fluorescence. If you manage to bring the molecule to a higher electronic state, an excited state, then it can happen that the Raman effect is much stronger. I guess Martin will talk about in the next lecture about that, resonance Raman effects. But on the other hand, this can involve also fluorescence when something is when the molecule absorbs something, then it also radiates, and this gives us the effect commonly known as fluorescence. And fluorescence is 3 orders of magnitude larger than Raman signals. And since we are talking about something that is very, very faint at all, so Raman scattering in comparison to Rayleigh is 1 million smaller than what we see here from common surfaces, then we know that fluorescence easily will be larger than any Raman signal. Here you see loads of fluorescence and only very, very tiny peaks of the Raman signal on top of it. So why are we using actually Raman? It seems so complicated, but it has also many advantages. So the position of peaks allow assignment to molecular bonds in the directions. We have quantitative information based on intensity. So that we see that in the following formula, so the Raman intensity is proportional to the incident light that comes from the laser and also to the frequency. Higher frequency, thus lower wavelength, would create a higher Raman signal, but unfortunately also increases fluorescence usually. But then similarly as with NMR, we have the proportionality to the number of molecules here in there, and also the polarization, of course, depending on whether it's a weak or a strong Raman molecule. but in particular, this correlation between intensity and number of molecules we can make use of in the quantification. We can therefore choose different lasers, for instance, against disturbing effects. We can choose glassware because glass is usually a weak Raman scheduler, which is the thing why we can also use windows and usual telecommunications equipment, which is much cheaper than IR spectroscopy. And the Raman activity is in particular low for water, which gives us an advantage for biotechnology. So how to quantify? First and very basic thing would be to use a peak integration. You just take the peak, integrate the area, and have a direct measure for the number of molecules according to the previous formulas we have seen. It's intuitive, of course, and very fast, but you can easily imagine this will not work when you have overlapping peaks or nonlinearities in the spectrum. What comes then into play is data-driven methods on one hand. First of all, partial least squares regression, where you regress certain features of the spectrum to certain quantities like concentrations, but you could also try for temperatures, etc. This is very, very easily done. You only need a large data set. And if you have nonlinearities, you're on your own. It requires high calibration effort in that case, and good training of the model, which is why I would like to introduce a physically motivated alternative here, the so-called indirect hard model, which is based on the idea to have pure component models, combine them in a mixture model, and then calibrate in order to derive the composition of your components that you want to determine. It is a physically motivated approach, however, and it can also deal with some nonlinear effects. However, it will also require some expert strategy in order to come up with a good model, but gives you the advantage of exploiting further data for other parts that have not been quantified. We will see that in the outlook. So the indirect hard modeling will start with a pure component model. The idea is that one peak actually can be resembled by a so-called Voigt curve or pseudo-Voigt function, which is a convolution of a Gaussian or a Lorentzian function. Lorentzian is much steeper, Gaussian distribution is much broader, but that depends basically on how the spectra has been recorded or what is due to the actual measurement. NMR usually has very strong, very sharp peaks. Raman has broader peaks, FTIR even broader. That also relates to the optics. In an ideal world, it would be only a very single intensity, like in gas phase measurements. In liquids, there's much more interaction and it broadens the peaks. What we then determine is the parameters of these peaks: position, the height, the width of the curve, and of course the fraction of Gaussian or Lorentzian. So 4 parameters for each peak. And then we can build a spectrum by summing up these pseudo-Voigt curves, including the parameters for the area that actually resembles then the quantity of molecules in the particular spectrum, in the particular sample. Having now the pure component, we can combine that into a mixture model, and by introducing certain weights here, omega-1, omega-2, omega-3, in order to mix pure component spectra into a sum of pure component spectra, the so-called mixture model. The optimization problem is basically that we want to minimize the difference between a measured spectrum, a measured area basically, at a certain wavelength. subtracted by a baseline. We'll come to that in later slides. And with the sum of all these peak functions that have the predefined model vectors of the individual pure component point functions. Having done that, we have these areas and its weights. We then need to correlate these weights via a calibration coefficient with concentrations of interest like molar concentrations or mass-based concentrations, etc. The beauty here of that calibration aspect is actually that it requires very, very small calibration sets only. So in principle, we would have a pure component model here at 0, maybe another pure component at 1 concentration value. And then we only need 3, 5, ideally only 1 in between in order to determine the slope of that calibration line here. Usually we take around 10 in order to make sure that we don't miss an effect, because of course we need to make sure that the linear relationship actually exists. If there's something else going on, we need to analyze for this nonlinearity. This is what in the reminder of this talk I'd like to show you briefly as a hands-on comparison here of results. So in the following slides, I'd show you some applications of peak integration, the very simple approach, the indirect hard modeling and partial least squares, two very simple spectra, but then advancing to overlapping peaks, extrapolation, and even unknown components. And we'll have an outlook on challenges like particles and fluorescence. So with peak integration, it's and this particular system here, a mixture of chloroform, ethyl acetate, and N-heptane. This is very simple. The peaks are very well isolated, so you can pick one of these peaks here for each component, and then you can quantify, and you see here in these plots, the predicted values in the back very much resemble the true concentrations here indicated by green stars. But as you can imagine, if that becomes more crowded here, it will not work that effectively. You see that here, for instance, with sucrose and fructose, two sugars of interest in particular for biotechnology. The fructose and the sucrose have very similar peaks because similar in molecular structure. Fructose is part of sucrose, of course. And so we have only very small differences that we can quantify. It works actually here in that case, but you see also a number of samples have been falsely predicted in these plots. And so although there is seemingly obviously a trend that is reflected, there's also very many samples that do not follow or that are not predicted correctly. We can do better with partial least squares. Here we come back to the examples of chloroform, ethyl acetate, and N-heptane. With partial least squares, you can easily quantify such a mixture. Of course, what is characteristic for partial least squares here that you have changes in the errors that are non-systematic. Yeah, so see, it's cloudy here basically. There are sometimes trends like this here. So although there's very good reflection, or the prediction is actually very good here in this case, it's obviously also a simple system, you lose the physical rigor to the original data. And you need to do the whole thing if you maybe change the instrument, etc. So that's what you need to be very careful with, because it's simply data driven. With indirect hard modeling, you would then model the individual components, chloroform, ethyl acetate, and N-heptane. and with the individual peak functions, create then a mixture model, and then you can do as well here. No wonder. But what is interesting if you do extrapolation in the individual, or in the beginning, I showed you the calibration strategy, and if you calibrate within a certain range and you go outside with data-driven models, you're basically on your own, and that exactly is shown here in that graph. So the true value and the predicted value differ largely by more than 10% of the value, and because the calibration has only been carried out up to 30% here, 35 in that case, and if you go outside, then there's a significant difference between true and the pre-LS prediction. IHM doesn't have this problem. Here we selected some validation samples as an extrapolation example, and since we have identified this line here, this calibration line, it can easily follow once more if once again if you're outside of this calibrated range, because it simply relates to the physics how the spectra are being generated. Same as with an unknown component. It could easily be that you don't know about every component that is in your mixture, and you want to maybe apply this mixture to that measurement as well. If you add an unknown component to a binary mixture here, now ethyl acetate and N-heptane, and maybe we don't know about the chloroform that is in there, then we easily see that this model breaks down. Here we have false predictions with the addition of chloroform when the mixture doesn't, or when the calibration doesn't know about it. IHM, that's not a silver bullet, but it can cope more with it. It can cope with it a little bit better than PLS. So here you see the very same example with IHM. And it's not that falsely predicted as with PLS. Alternatively, maybe that's already also an outlook. We could also add dummy models that account for the components that are unknown and doesn't need to be in the mass balance of the calibration. That's what you cannot do with PLS so easily, but due to the fact that we model explicitly the spectra, we can also account for such effects. And such effects also is the content I'd like to show you on the last slides now. I said it's much more complicated, in particular when it comes to turbid mixtures and particles, etc. Here's an example from polymerization. Very challenging thing, because as you see, before the reaction it's clear, and after the reaction it's even more turbid than milk. And we were able to quantify the monomer content and the polymer content as well. So this is an indication, or this is just maybe an idea here, that Raman spectroscopy is not only valid to cover liquid concentrations, but can also detect solids, and in this case it was also validated with focals, a quasi-elastic light scattering, which told us that it's very much in line with what's usually analyzed offline in the lab. Same as with particle sizing from Raman spectra. So in this publication here, we applied a hybrid modeling approach. First IHM in order to quantify the concentrations, the polymers and the monomers, so what is readily known and detectable, and then we had the rest, which is basically the spectral error. We took that, we analyzed that noise basically with a data-driven tool in order to quantify particle size. And for this particular system, it worked very well. You see the goodness of the fit, which was even amazing for us. but it's a combination of a physics-informed model and a data-driven approach. And then you could also analyze for the flow versus batch reactor setups and improve or support the design of such things, because you know about what is particles, what is liquid concentrations, and you can measure at different positions in order to mimic then reaction progress and analyze for optimal operation. One thing I'd like to, which is the last phenomenon I'd like to show you, is the promised fluorescence. In particular, when it comes to colored samples with some from realistic sources, thick juice, for instance, from industry here, very, very turbid, very, very dark. That gives you some signal that is, definitely with some fluorescence in there. It's not so easy to quantify. So the background is definitely hard to identify. Whereas glucose here has a very nice and shiny spectrum. The same is true if you go for fermentations. The broth and the supernatant differ hugely just due to the fact that there's particles in there. And so these particles block actually the Raman light that is collected in 180 degrees backscattering setup. Or here with fructose, where you also have underlying fluorescence, as can be told by the increasing background, which is kind of rather moderate in this case, but it could also be much worse. In the middle, you see an example from a real fermentation where you hardly see anything else than just this broad background of fluorescence. But again, by certain mathematical corrections, you can correct for and clear this fluorescing background from the Raman data and still isolate the Raman peaks that are still on top of this signal if the signal to noise ratio is sufficient, and then you can still quantify fructose, sucrose, glucose, and the products as effectively as HPLC does in offline analysis. So last slide, I promised to also have to give a note on the application in digital twins, why it is so important for digital twins. Of course, a digital twin would drive us to action. It would not just monitor and quantify. So what we have in our setup is, of course, a process logic control that controls all the valves, the pumps, etc., and sets pressures and flows, etc. And of course, then we have the advanced spectroscopy, Raman, NMR, in order to derive concentrations. These concentrations can be derived inline or in real time, also via APIs in our software, where the models can be evaluated directly. So it gives us concentration data in real time, and PLCs, our PLCs have an OPC UA interface, which is an open platform communication standard in order to exchange data points between process logic controllers and external sources. And in our case, we set up a MATLAB model here that calls in the client and server architecture the process data here, and can also process the data that it gets from the Raman or spectroscopic devices, and then we can set up simple models or more sophisticated models in order to vary set points and optimize the process online. That would be then the vision for the digital twin, and hopefully you agree that PAT is a very key measure for that. So in summary, we have seen the principles of Raman and NMR. And in particular, it's important to know that they are all based on the proportionality of the area in the spectrum to the number of molecules. So a quantification can be directly applied. We have seen a couple of techniques in order to quantify. First of all, the peak integration, which is simple and very intuitive, but not very robust. Partial least squares is state of the art, and indirect hard modeling, I think, is something that would open up opportunities for us, in particular when we use physics-informed modeling in combination with statistical or artificial intelligence modeling in order to unlock features that even have not been addressed so far in Raman or biotechnology. Thank you for your attention.